It's 1 past the hour. So hello, everybody. Thank you for joining this session. This session is a workshop about Yugabyte SQL execution internals. And it's, well, first about me. My name is Frits Hoogland. As you probably can hear and can see, that's not a native English name. I am Dutch. And I'm a developer advocate from the Netherlands. And these are my LinkedIn, Twitter, and my blog. And I'm going to talk about SQL execution internals. This workshop works best if you've attended Frank Pechot's session 1 hour ago. And you can look it back if this is the first session you join, which was about how to create tables and how to use tables in Yugabyte and how to set them up for optimum performance. And that is something that I will talk about and will stress about in this session. It doesn't make sense to start looking at internals if the basic principle of what you're doing does not make sense, which means quite simply that if you have if you want to search a single row in a really large table, and you have a filter and you know which row it is, it probably makes sense to use a unique or a primary key index to find that row and not use a sequential scan. So a full scan of the table to get that row. If you do not first stick to that principle, then and do things in a really inefficient way and scan gigabytes of data to find a single row, it doesn't make sense to then try to tune this non-optimal way of accessing the data. The correct way is to first use the available mechanisms in SQL and in SQL in Yugabyte to first set up the database in a logical, sensible way. And then once that is done and things don't perform as you expect, then you will start looking deeper into what's happening. And that is what this presentation is about. So this is a technical session, so I will not be talking about high-level concepts, but at more low-level concepts. And what I want to show is a methodology using tools, and I will be using one tool which I will be introducing in the next page, which is YB-Stats, to get an understanding of what is happening in the different layers of Yugabyte execution. And that will help you to understand. And once you understand something, you can tune it. You don't tune and then try to understand if it helped. You should first understand what's going on and then tune it based upon that understanding, because that understanding makes you go tune it in the right way instead of in the wrong way. And it also removes guessing, because guessing has the same principle. Just fiddling things around might get you in a worse place than a better place. And like I said earlier, for this line, there is no substitution or alternative to SQL tuning. You must logically tune your data model and the queries you're using. What I will be showing is essentially a methodology and a look into to hope to inspire you, if you're running something, to also start looking deeper into execution in Yugabyte. And this tool is YB-Stats. And what YB-Stats does is it fetches and stores Yugabyte cluster metadata for investigation and research. And not only investigation and research, you can also use it eventually, if you have a support contract, to get it to our support and discuss things with support and even get it to development. Because the data that YB-Stats takes is the exact same data that we use in our paid platform, which shows graphs about how the database works, etc. It all comes from the same source. And in this presentation, YBStats is used to investigate a cluster and showcase usage. And hopefully, and it builds up an understanding of what's going on. If this is the first time you're looking into Yugabyte DB, you probably cannot and will not directly understand all that's going on, because almost by definition, any computer cluster that I've looked in the last 25 years is rather complicated, because you have multiple computer systems which needs to work together, and that by definition is complicated. So use this presentation to try to build a basic understanding, and then go try and experiment for yourself to see if you can recreate and redo the things I've done and see the same, and look into other issues. That is the task I'm setting for you if you're interested in this. It's probably, it took me quite some time to get a logical understanding and a logical flow and understand the different layers, which I will be presenting about. So I do not expect you in 1 hour to get a full 100% understanding. That is why there are a gazillion IT sessions and a gazillion IT courses on how things work. But what you can do is start off with what is in this presentation and try to build an understanding. The link for YBStats is here. YBStats is currently not part of a Yugabyte DB default install, but we are in the process of making it part of a standard install, so that YBStats is always there. Because like I said, our support is also using it to investigate things. And one of the fundamental important things which would otherwise be quite hard is it takes a snapshot, and that's also the basis on which we will be working. It creates a snapshot of a certain point in time. So if you create a snapshot, then do something and create another snapshot, you can see the changes that whatever you did in between has done to the cluster. After YBStats is installed, this is how it can be executed. So if it's installed, you execute --snapshot, which will create a snapshot. And you can specify the hosts to snapshot the data from. So this ought to be the IP addresses of your Yugabyte cluster. And these are the IP addresses of my test cluster, and that's also the cluster that I used to perform these tests. If I also advise to use an empty directory to start snapshotting in, because after setting --hosts for the hosts, --ports if you use any non-default ports, and or --parallel to use YBStats in a more parallel way, it will write a file called .env in the file. And it will use that from then on. So you only need to specify the hosts and parallelism once. And from the current working directory, it will then read the env file and use that. So you don't need to specify it all the time. That is to try to make it as simple to use as possible. Also, in the source GitHub repository of YBStats, you will find RPMs to do an RPM install if you use YBStats on a Linux host inside a cluster. That is the way it's most commonly used. And there's also a way in which you can use Homebrew to install YBStats on your local MacBook. If you're using a MacBook, obviously, to use your MacBook to create the snapshots. That's all what I provided. Okay, so YBStats for creating the statistics to look into things. Now let's go up to the next logical step, and that is the logical architecture. This is something that Frank also touched upon, And this is kind of a logical drawing of how a Yugabyte DB cluster looks. For Yugabyte DB, a client shown as Postgres client over here, that's what this square tries to represent, connects to this square, and this square is meant to show a server, and it connects to this square which says Postgres, and that square Postgres is the Postgres compilation that we use with Yugabyte DB, which is modified by us to work with our DocDB storage layer, DocDB database. So you connect to a Postgres instance. This is 100% the same as if you would connect to a regular Postgres instance. And the reason this is 100% the same is we use the Postgres source, and on the upper layers, on the SQL layers, we haven't changed anything. So you're truly just connecting to the exact same code as with a Postgres server. And therefore all the Postgres tools that you're familiar with can work with Yugabyte, because that is 100% the same. When a client establishes a connection, it creates a connection, which is a dedicated process, which is commonly used and which I also will be calling a backend. So if I talk about the backend, that is the process which is created after you've logged on to a Postgres server on the server side. Starting from a Yugabyte DB 2.13.1, any communication into the Yugabyte DB cluster from the YSQL backend or Postgres backend is done to and via the local tablet server, and that is what this square meant to represent. So this dash, this line, is a connection, a network connection from the Postgres client to the Postgres backend, and this connection is a network connection from the Postgres backend to the local tablet server, which is one of the Yugabyte DB DocDB servers. And this is why there is a single line. If communication is necessary beyond the local tablet server, then the local tablet server will initiate a connection to a remote tablet server and fetches the data from the remote servers on behalf of the local tablet server for the Postgres backend. So that is how it uses. What this drawing shows is the minimum setup for a replication factor free cluster, or the minimum logically sensible setup for a local replication factor free Postgres cluster, which means that you have 3 copies of your tablets on 3 servers, and that's why there is 3 squares. So this is a really basic introduction, but hopefully this will also start making more sense if this is completely new to you when I explain further. YSQL layer. The YSQL layer, from which we saw a little part, consists of Postgres, which is enhanced to talk to Yugabyte DB master and tablet servers. The master servers store the Postgres metadata or catalog, and the tablet servers store Postgres data or user data. Master servers manage the cluster topology, so the master understands where all the clusters are, where the other masters are, and where the tablet servers are. It provides cluster services, and for cluster services, think about, for example, if you want to create a tablet with a number of tablet pairs, where these have to be placed and where the tablet leader needs to be to make it as evenly distributed over the physical servers as possible. And the master servers store the Postgres catalog. And these are simply stored in tablets, just as the tablet servers would do. And in that sense, the master server is kind of a special tablet server. In a Yugabyte DB cluster, there always is one master leader, and that is the one which actively performs the services. And replication factor -1 master followers. And these work in a raft group, and Raft is the consistency protocol for dealing with multiple copies, which Frank also talked about. And if the master leader, for whatever reason, cannot continue to function as leader or function at all, then the remaining followers, the remaining masters, which are the followers, will elect a new one, and then the elected new leader will perform the leader tasks. That is how it works. And this is important because if you log on, you must fetch metadata in order to be able to start up your backend. So if you log on to YSQL, you start a backend, and that backend needs to fetch some metadata before it can do work. And after you've logged on and this metadata is fetched, then any operations that you want to do, which would be quite typically executing SQL, needs to fetch metadata and validate this metadata before you can do anything. And this also must be fetched from the master leader. However, once all necessary metadata is fetched, the master is not in the critical code path for doing reads or writes. After this data is there, and once it's fetched from the master, it will be cached. Then it can function on itself, and your backend can talk to the tablet servers without requiring talking to the master. Now, this is the same picture as I've shown before. If we then add the master service, this is how it looks like. The master service will be on each of the 3 physical nodes in the cluster. And why are they there? Because if it's replication factor 3, there need to be 3 masters, and one of them will be leader. And the fact that this tablet server is aligned to this master as a logical depiction of using the master services, this one is probably the master. What would happen if an extra node is added to this cluster? If an extra node is added, you will need to notify the master that an extra node has been added, and these services must be up, and then the master will register it. However, the new node then will not have a master server, because the total number of master services that you will have in a cluster is equal to the replication factor. And if the replication factor is 3, like in this logical case, then the number will be 3, so a new node will not have a master server, but it will have a tablet server which will have a YSQL alias Postgres instance. So that is logically how it works. If you want to understand where the master services are, there are a couple of ways you can do it. Quite commonly, the most common way of doing it is going to the HTTP page of your cluster, which is either 7,000 or 9,000, and then click in the user interface that's there and look at the master, and then follow the links which will tell you what is the master server. However, the important part is, obviously, quite logically, if you go now to a cluster and find out who is master, that means that that is the master at that point in time. If you create a snapshot and then use the -- print masters and then a snapshot number, in this case, it's snapshot number 0, it will take the master information at the time of the snapshot and print it. This is important because this will allow, for example, if you have a situation where you're not sure whether something is happening to the master or the master gets overloaded or whatever, you can take a snapshot, perform the task that you are anxious about or where you're not sure about, and then perform a snapshot again, and then investigate the master data from before what you've done and after what you've done. So the snapshot is the status of a certain point in time, whereas if you're looking in the web UI, you will be looking at the current situation, which might not be the same situation as before or after a certain situation that you're investigating. Another thing to say about this here is The source host is an IP address and then 7,000. 7,000 is the default master port. So this is the source host is a master server, and this is the information which is available at that master server. This is another IP address with 7,000. So this is another master server, and this is the master information as available at that server. Now, why do we need this information multiple times? Well, one of the cases which potentially could happen, especially if you are having networking problems, is that not all masters have the same information. And the way to be able to investigate that is using YB stats and then looking at this information for the different masters and see if that information is 100% identical. Having said that, if your cluster is reporting to be healthy, then this information would be identical on all masters, and with a replication factor 3 cluster will be the same on all 3 masters. Then the next thing, if you look at this data, it prints the available information for the registered masters, and with a replication factor 3. And I'm repeating myself a lot. We have 3 masters, so you have 3 points of information on this single master about the other masters, and about 2 masters remotely and 1 master locally. And it will tell you that there is a follower on this RPC and HTTP address. There is a leader at this RPC and HTTP address, and a follower at this at these addresses. The thing which this doesn't say is you can use DNS names or host names, like it's being done here, whilst I am using IP addresses. So you have to know where a host name maps to, and in this case YB-1 maps to 192.168.66.80. So this page is saying that this server at this snapshot time is actually the master. So hopefully this already gives you an idea, especially if you have a background in operating and investigating clusters, why this is useful. Creating a SQL connection requires a database client to initiate a fork of the postmaster to create a backend. And like I said earlier, the new backend must perform some bootstrap actions, such as loading an initial set of metadata into the rel cache and the cat cache. And the rel cache and cat cache are 2 caches which sit in every individual backend, and these must have an initial amount of data to be able to function. To load these require communication with the master leader, which is executed via the local tablet server. If you're wondering that this looks clumsy in the sense of having to have some local data first, this method is exactly how Postgres also creates a backend, and we simply reuse that method. Another really important thing, both Postgres natively and YSQL, because we completely reuse Postgres, do not keep any statistics or timings about logon. So you cannot tell from a statistic like number of logons how much sessions have been logging on. And this is a logical representation of it. Say you've got a Postgres client and this square represents a server. If you want a Postgres connection, you connect to the Postgres port, which by default is 5432 for Postgres and 5433 for a Yugabyte DB. You create to the postmaster, and the postmaster forks a backend. That backend at that point in time, like I just described, is not ready, and it needs to perform some work for the cache, for the initial filling of the caches. What it does is it needs to fetch data from the master leader, But for the way it works, it creates to the local tablet server, and it asks the local tablet server to fetch this data from the master leader. It then proxies these requests back to the backend, and it fills the caches. And then once the initial data is in the caches, it sends back an OK ready for queries. It's queue ready for queries back to the Postgres client, and then the backend is ready. Like described earlier, the backend communicates to the cluster via the local tablet server, and for the tablet server, and why this is important you will see later on, the master communication is remote communication, even if the master is on the same node. It is a different server, so it will perform an RPC network request to fetch the data. And because the logon requires the master data to bootstrap the backend, so to get the initial set in the backend, there are statistics on the tablet server. And I will be explaining a bit more about them. But this is, again, using YB-stats and now saying snapshot diff. So this is also what is done here is a snapshot is taken on an idle cluster. A single backend has been logging on, and then another snapshot is taken, so that we have everything in the cluster, all the data from what happened in the cluster in the statistics, so that we can look at what is happening when a session logs on. Now, so, and apparently this happened between snapshot 1 and snapshot 2, that's begin and end snapshot. And I only want to look at the tablet server, which is the local tablet server to the Postgres, to the postmaster that I'm connecting to. And a simple way of filtering out only the tablet servers is saying that a host name must match with 9000. Because the host name looks like 192.168.66.80 colon 9000, filtering on 9000 means we only get a tablet service. That's how it works. And I shortened this IP address just to get more screen estate for the statistics. Then the next thing that I do is I perform the switch --stat name match, and --stat name match is a filter for the statistics, for the statistic name, and the statistic name has to match with PG client service. Now, the next column here in the snapshot diff output is the type of statistic, and this is a server statistic, and there are also tablet and table statistics. Then this one is the statistic name, and the statistic name here is YBT server PG client server get database info. I've also shortened this a bit to get more screen estate for the statistics here, and the full name is handler latency YBT server PG client service get database info. So if you try to replay this and do this, you will see some more statistics which are not relevant here, which have PG client service in the name. And you will see that this statistic name is a bit longer. Well, I will be using these statistics a lot, so it's really good to pay attention to this. This first number here is the count of the statistic getting triggered. So the tablet server got one get database info PG client service request. This number is the number of these requests divided by the time in seconds between the two snapshots. So that's apparently 0.2 get database info triggers being triggered per second, and that's why it says -s. And then these next two statistics are not the amount of this statistic getting triggered, so the count, but the payload of the statistic, which is called sum. And these sums are, and that's for almost any, but not all handler latency statistics that is in microseconds, and that's why this says US. This is the total number, the total latency, so that in microseconds for get database info, so to respond to the client for a get database info request. And because there is only one occurrence of it, the average obviously is also one. So that is how that works. And I will be using the handler latency statistics a lot. So if you understand this, you're good. What is interesting about get database info is a statistic, is a call which is triggered by a backend whenever a backend enters a database. And the most common reason for entering a database is a session logging on, which means you can use this statistic quite well to calculate the number of logons to your database. So I said previously, and this is, I think, being seen as an issue by a lot of people, and some people found workarounds, but there isn't a really simple solution, as far as I know, without starting things like auditing to understand the amount of connections which a Postgres server gets. This statistic will tell you. There is one caveat. If a current session connects to a different database, then it will request database info for that too. So then this statistic is triggered. So that is the caveat. But in general, this is quite a good statistic to understand, and it is actually really useful. Then there is this statistic heartbeat, and this statistic heartbeat is kind of an odd one because this doesn't add to the latency of a backend request. If you're logging on, you have to wait for get database info. So get database info is one of the requests which you're waiting for, and that's not an extremely long time. It's less than a millisecond, but you're waiting for it. Heartbeat is not something you're waiting for. Every Postgres backend has additional things running, which are additional threads, which are by the Yugabyte specific part of the Yugabyte cluster. And every backend will send a heartbeat to its local tablet server every 10 seconds. What does that mean? So in that sense, this is not a really interesting statistic. However, if you take the average amount of heartbeats and you divide it by 10, you get the average amount of sessions in a cluster, provided you took a big, the time between two snapshots is big enough to get a good overview, because if you do it less than 10 seconds, then you cannot have all the heartbeats of all the sessions, obviously. So if you have something like 10 minutes, then you will have a good average, and then, do it times 10 to get the average amount of connections. Having said that, the previous to last and the last version of YB Stats now captures the RPCZ endpoint for the master, the tablet server, for YSQL and YSQL. And what the RPCZ endpoint shows are the connections. So that is actually a way better way, and it will show you way more specifics about the connections. But that is a recent addition. So if you're using an earlier version, this the RPCZ endpoint is not on the statistics and therefore cannot be used. And then using heartbeats can be used, but now this is not necessary. Then the next thing is open table, and open table is something that a stock Postgres backend also performs. If you need to query a table, which is both true for a catalog table, so it happens during logon, where you need to query some catalog tables to understand some information, but also for user tables. For any table which is not opened yet, you need to perform a request to the master leader, to the catalog, to open the table and store some metadata about the table in the backend in order to query the table. This only needs to be done once, but you need to do it at a certain point in time first. Once you've opened a table, then the next step is that you can request data from a table. Requesting data from a table is performed using perform. So PG client service perform means that a request for data, which will be a SQL request, is that a SQL is executed. And because this is logging on, so at this point in time, the session wasn't ready. It was just getting the metadata to get ready for user queries. This performed queries against the Postgres catalog. So apparently 2 queries were executed, and for that it needed to open 9 catalog tables. So that is how this should be looked at. Having said that, and this is something which I actually only recently found out, which in certain cases might be quite important to understand. The very first logon to each individual database on each server in the cluster after startup of the postmaster will perform extra work, and that is really only one in the lifetime, will perform extra work. This is identical in Postgres, but it is less visible. And the amount of work it needs to do is relative to the number of objects in the database the connection is connecting to. This extra work which is performed is reading the relations data and building a file in which it formats this data in a cache-ready format. And the file it writes, this file which is created, is called pginternal.init, and it will write it on the server, and all successive logons which happen after this for this database use this file. And for another database, a pginternal.init file specifically to that database will be written. And this file contains the relations cache. So instead of querying it from the server, it reads it from this file. And again, this is not something that we invented. This is something that is happening in Postgres too. Why is this important? This is important because if you're repeating, if you found something on a server and you repeat a test on a local server, there is a fair chance that you've just started it up to replay your test case. If you then do not take, and if this is about performance, and you do not take this into account, you might be led to think that performance is worse than it actually is. And to give you an indication, because of the RPC calls, creating a backend takes approximately 20 milliseconds. And this first time logon on a relatively empty database takes 200 milliseconds because it simply needs to do more work. This is also important for if you're doing things like micro benchmarks, etc. If you just log on and perform a test 5 times, then this first high logon time might actually negatively bias your tests. So you have to understand that this is happening. This is something outside of a second point, and the second point is that once your backend is ready and you start performing queries against user data, this user data requires to fetch the metadata for that. So that is also a first-time penalty, but this penalty is the very first connection on building a cache file and then using this cache file. And the penalty I was just talking about, which is again identical to how Postgres works, but is less visible in Postgres because it can use the Postgres shared buffer cache locally, and everything is done locally. So you do not notice it that much in latency. It is visible in the latency, by the way, but it's less visible. Okay, YSQL, so the Postgres version which we bundle with Yugabyte, contains the Postgres source and a code base called pggate, which we call pggate, which provides all the Yugabyte specific functions, such as getting catalog data, getting data via RPC. The way this works is it adds threads to every individual backend, and these threads communicate with the local tablet server on getting the data. Yugabyte DB externalizes some pggate level communication statistics, and it also externalizes pgstat statements in the dash statements endpoint and pgstat activity in the /rpcz endpoint. Now, another really important thing, every query in Postgres, and this is both true for Postgres and YSQL, needs to go through 4 principal phases before it can be executing on data. And that is, it has a parse phase, and the parse phase is the syntactical parse, and the syntactical parse means it's using actually the very old Linux, Unix utilities lex and yak, just to create an execution tree from text. So it takes text, it passes the text using lex and yak, and it tries to understand if it's valid SQL and what tables you try to access, etc. Because this is simply done by rules, and it understands you want to query a table, but it doesn't look at a table or whether this table exists. It can do it completely local without any understanding of how your database looks like. And that's why there is a dash here. This doesn't require any catalog, dash, alias, master lookup. The second phase is called the rewrite phase. And the rewrite phase does 2 things. It does another parse phase, which is the semantic parsing. And the semantic parsing is it already built an execution tree, and it now understands what objects you want to access. But now it needs to look whether that object exists and whether you have access to these objects. And that obviously requires the catalog, because it needs to understand if something is there and what are the rights which are set on it. So that's why there is an asterisk here, and it performs rewrite. Rewriting is one of the things which needs to happen for a view. A view is a logical query, and a view at any point in time in any database, in any relational database, needs to be brought back to the base tables it's actually dependent on. And that is what rewrite does in Postgres. So once we've then got a parsed query tree, it goes to the planner to create an execution plan. And in the planner phase, it needs to investigate metadata about these tables, because the planner in Postgres is quite heavily cost-based. And these costs are stored in the catalog. So therefore, the planner needs some extra data. And again, once this is done once, it's not needed again. So the planner takes up the costs of the different objects in the query and then tries to figure out the most efficient way as seen from the cost. So if the costs are not correct, it might make a plan which does not make sense for you. So it does that. And once the planner created an execution plan, it goes to the last phase, and the last phase is the executing phase. And that is where the executor takes the execution plan that the planner created and actually execute it, and where it performs the things you want to do with the data. Now, there are 2 important things to say about this. I will not go deeper into that, but if you're using the extended query protocol, what the extended query protocol calls parsing is parse and rewrite for these two phases. So that's parsing. What the extended query protocol calls bind is what is the planner phase, and what the extended query protocol calls execution, obviously, is execution. If you create a prepared statement, then the parse and rewrite step is materialized and stored in the backend. So it's not visible outside of your local backend, but it is stored in the memory in your backend, so it can be used again. So all you then need to do is plan and execute. And then probably the most important part of this slide, once you start executing, it Postgres times the time spent actually executing the execution plan which is the result of your SQL. The time spent in the executing is the time which is visible in pgstat statements. This is really important because if you're executing a query for the first time and these steps need to obtain more data from the master, and especially if the master is not really close by or on the same server, then there could be some time involved before this metadata arrived and is available for these phases, which means that there is extra time involved in the overall execution of a statement. But because this is mostly sorted before it gets to the executor, pgstat statements might give a very low latency, whilst overall you're seeing high latency. One of the phases you can recognize this is especially that if you're executing it again, if it's then fast, which means then it means quite logically that you could take advantage of caching this catalog data and then execute it again. So that is a really important one if you're seeing this. If you're using the web UI and you're looking at slow queries in the web UI, that is using pgstat statements too. So you're not seeing the full time which is actually spent on executing. You're on the overall execute. You're only looking at the time spent by the executor. pggate acts as a layer between the actual Postgres execution and the tablet server. And for simple SQL, pggate statistics will be quite often roughly identical to the pgstat statement statistics. Now I'm going to look into and try to dive into the different layers. And I do not expect you to soak this all up and be able to reproduce it. What I urge you to do, if you're using Yugabyte, want to use Yugabyte, or want to learn about Yugabyte, is to install Yugabyte on a replication factor-free cluster, or use a preset of one or whatever, which is idle, so you can perform your test. Install YB-stats, and installing YB-stats should not be too hard, because that is Rust code which can quite simply be compiled, and there are RPMs, and there is an OS X formula for homebrew. And you can create the large table that I created, and large is just a name, and maybe it's a silly name, but because large is relative to the size of the rest, obviously. And it is use create table as select, and what I do is I select ID and then a column repeat, for which I repeat X 500 times, simply to create padding for the column. And I use generate series 1,000 times. You can also experiment with a smaller series of a bigger series, etc. That's all up to you. I on a tiny cluster on my notebook for testing, I used 1,000,000. So that is what I did. So once I've created this table, what I did is I performed a YB-stats snapshot using -- snapshot, so that the snapshot is materialized. then gone into YSQL, but you can also use PSQL to connect to the local Postgres instance in the cluster. I set paging off using a \p set pager off, and then executed the select star from large. And once this was ready, I performed the YBStat snapshot again. And now let's see how that looks like. The first thing that I did is, oh, by the way, the snapshot numbers for before the select star and after were number 1 and 2. And what I do is a snapshot diff, and a snapshot diff takes the performance figures from the second snapshot and subtracts the values from the first snapshot and show you the result. And I'm using the hostname match trick, which I showed earlier for T-Server, and I now use a port 13,000, and 13,000 is our default YSQL port. And by using hostname match alias filtering for 13,000, I only get the YSQL statistics. If you look at the bottom, then this is 192, 168, 66, 80. Again, I shortened this to create more screen estate. There was one execution of this statement, which I already said is select star from large, and the total time in this one execution is 12,332 milliseconds, alias 12 seconds. And because it's one execution, the average is identical, and it dealt with 1 million rows. These statistics are the pgGate level statistics. If you look at the pgGate level statistics, it said it had one occurrence of a select statement of a single shard transaction with underscores. These two are identical, but for reasons of compatibility, there are both there. And it was a transaction, and all these have the same time, one execution, and the same amount of rows. So a SQL statement could categorize in multiple for multiple of these statistics. So you cannot add them. This is all the same. So this is the first level. There isn't a lot of exciting things, except for you can see the number of queries which are executed and the actual queries. These are bound by the limits of pgstat statements, and I believe the default limit of pgstat statements is 500 sequels. So there is a limit there too, but especially for looking at test cases or at moderate usage, this should be enough, and then you can look into this. There is one additional thing, and that's for the people who are very familiar with Postgres. The pgstat statement stores, shows SQL text, but it actually stores the pass tree of a statement. And because it stores the pass tree of a statement, what you could see in pgstat statements is multiple sequels being individual rows in pgstat statements. And well, the reason is for what I just explained is because it stores pass trees, it stores the object by OID. So if you create a table test and perform a select star from test, then delete this table and create a table test again, and then perform a select, you will see this select on test 2 times in pgstat statements, because these have different object IDs, and thus for pgstat statements, these are 2 different sequels. Whilst for us humans, by looking at the SQL which the Postgres engine reverted back from this pass tree, it looks like, and it is actually completely identical SQL. So that is another thing, another caveat, which is important to know if you're looking in these things. But we've got a timing here. So, and the timing is vitally important because this is the actual latency, and you see the pgGate level timing, which mostly is identical. If you put this in a logical overview, and I'm sorry, it's not a stunning, beautiful graph, but hopefully it is good and simple enough to get the idea across. This is the logical representation of the local tablet server. This is the client, and this is the post-rest process. The post-rest process contains the different phases of execution and pgate. And what I just shown is, in execution, I spent 12.3 seconds, which I also probably, well, not probably, I spent time in parse, rewrite, and planning, which is not visible in pgstat statement. So that is why this is explicitly pgstat statement, and this is pgate. Pgate is, well, as good as identical. From pgate, we go to the tablet server. And the first thing, well, actually, in the tablet server, we go through a reactor, and the reactor will assign a perform thread. But that is visible in YBstats, because YBstats shows all available statistics, and it provides them, it shows them in an unfiltered way. So if we add something, it will be in YBstats. But because this assignment, especially if you're looking after a single query, is almost instantaneously, I did not add it. So the next thing, what we will see then, is the perform thread. So whenever a YSQL process, or a Postgres process, however, whatever you like to call it, needs to perform a DocDB task, such as querying data, but also fetching metadata from the master, it requests these tasks from the local tablet server. And these requests, as we also just shown, are visible as PG client service statistics. And this is, again, this is now for the select star from large as a table. And, well, it's almost identical. It's a snapshot div for begin and end snapshot 1 and 2. I now match 9,000 because I'm now looking at a tablet server, and I've got a cluster of 3, but because I only operated a single SQL on host 192, 168, 66, 80, I only see statistics on 80, on host 80, and I'm looking for stat name match PG client service. The heartbeat, again, is just the heartbeat. It doesn't add to any latency. I performed in this session, I performed it for the first time. So open table is 1, that's for the table large, and it took a low amount of time. And after I've opened the table, the select star read all these million rows, and reading a million rows required 979 occurrences of perform, which in total took 11.2 roughly seconds. And if I divide it, it's an average of 11 milliseconds, but that's not important here. The important part is, if we now stack this as the next level, at the perform level, so at the first actual level in the tablet server, it spent 11.2 seconds. The difference here, obviously, is the networking time between pgate in the Postgres process and the perform thread in the tablet server. This is also a very useful statistic to look at, in the sense that you can roughly, because it's we do not look at all the Postgres levels only at execution, phases only execution, but if perform has a really low time, as select has a very high time, then it might be worth looking at the explained plan of this query again, because it might be doing a lot of work which doesn't require any tablet server interaction at all. So this is another thing which is really handy to look at. The next one is the local and remote execution decision. Inside a perform thread, the next thing that happens is it will determine where the work needs to be dispatched. And this dispatching can be seen with the statistics which are marked YB client. And it will be shown as local and remote. And local means the same tablet server. So it's local doesn't mean the same host, but it means the same tablet server. And remote means a remote tablet server or the master leader it needs to communicate to. And there is a downside. YB client statistics currently are measured with a more coarse clock than the other statistics. So these can deviate a bit with the other statistics, which are measured with a more granular clock. Now, YB stats is invoked in the same way with almost the same arguments. Only, and this is because you can use a regexp, or it uses regexp for the matching. I use the regexp YB client or perform. So what I'm now seeing is the YB client statistics. And again, this is only host 80, so the IP address ending on 80. I'm seeing the perform, which is the total time, and I'm now seeing local for roughly 1/3 of the occurrences of perform, and remote for roughly 2/3. So that is a nice even distribution of the work which entered with perform. And also if you look at the times, it's 11 somewhat seconds, and this time is roughly divided in 1/3 versus 2/3. So that looks nice and clean relatively. So if we add this here, we can see this. And now we're getting to the tablet server service. Once the dispatched work has arrived at a correct node, and that's what it does, it will perform the work as general DocDB requests. And general DocDB requests tend to be read or write. And that is why this layer is called tablet server service. And this is the actual time which is spent in DocDB for performing a read or write request. So if we then take the statistics, so we've got a perform thread here, we've got the 2 YB client threads for local and remote here, we've got 3 tablet server service read statistics for the host ending with 80, 81, and 82. So this is the dispatching. So it's nicely evenly divided over the 3. They roughly get each the same amount of requests, and they roughly equal in time. And because they're roughly equal in time and in the amount of requests, the average time per request also is in the same ballpark. So now we know that we're doing reading, and this is the actual time which an individual tablet server spent on performing what it ought to do. And in this case, that's reading. So let's add that here. Once the tablet server has performed its logic, and it does a lot more, which is beyond the scope of this talk, just to try to keep it still to some points and to a targeted investigation. It does performing its I/O to the actual database that sits underneath DocDB, which is RocksDB. And there's an enormous amount of things to say about RocksDB and about log sorted merge tree, which can be said. And Frank gone into it for the statistic that Frank's used for the amount of work done. But the important part here is that the LSM tree and RocksDB as an LSM tree implementation performs the actual physical writing. By doing that, and this is different than standard database. For a different database, you can perform a cached I/O, which sits in the buffer cache of a database, or you have to read it from disk. And in an LSM-3 database, and in RocksDB specifically, your data can sit in 3 places. And the 3 places are the mem table. The mem table is the first level of where your data is stored if you start inserting data into a table. And if the mem table is full, the mem table is made immutable and is written to disk as an SST file, a sorted sequence file. And a new mem table is created. And if data is requested in RocksDB, in Yugabyte, in RocksDB for something which is sitting in an SST file, it will or can be cached in the block cache. And this is quite important because this means that the caching, the fundamental cache layer of the database DocDB or the database YugabyteDB is sitting inside the tablet server. It's not sitting inside the MySQL Postgres service. So if you request data in a session, it will fetch the metadata from the master and cache that locally. But if you execute that again, it will need to request the data from the tablet service again and get it to the local backend. It does not have access to a shared cache sitting in memory for this backend. This is also one of the things which is principally different with Postgres, where frequently used data is sitting in the buffer cache, which is absolutely locally. We are looking into solutions for this, but this is the current state of YugabyteDB. However, we do cache in the tablet server. So in our case of querying data, we can use the cache sitting in all the 3 different tablet servers and request the data from the RocksDB block cache. Blocks are compressed physically stored compressed on disk, and they are stored uncompressed in the block cache. So therefore, this is a bit more lightweight, even if you have a really fast disk. Another thing is our statistics currently are not in a way that the statistics between the mem table and the RocksDB block cache and physical I/O are in the same format. In fact, they are both not in the way that I would like them, but we are also working on that. And that is the mem table has statistics about reading documents, which is essentially columns of a table. So if you have a really wide table, a lot of gets could still mean a row. And if you have if you have a table with only a few columns, then reading a lot of performing a lot of gets will probably read a lot of rows. So and the block cache and physical I/O is measured in blocks. So it is not easy to get something definitive from this, but I've worked something out, and by looking at the physical I/Os, you can roughly determine the amount of physical I/Os, but it is bound to limits, and it's not 100% exact. And this is how that looks like. So this is once again the same query for the snapshots, for the snapshot diff, and I've extended the stat name match for YB client, perform, tablet server service read, RocksDB block cache hit, and SST read. And what we're now seeing is the perform thread, with the total time, the YB client local and remote thread, which separates it from local and remote. So we can see that this is evenly distributed. We see the actual reads taking place, and most importantly, the time spent in these reads. And then what we can see is we hit the block cache. So the block cache is being used, and we performed physical reads. RocksDB SST read micros is the number of microseconds spent in reading from an SST file. The amount of IOs is roughly equal, and there is a certain amount of time, and if we divide these two, the average time per SST read is 0.3 milliseconds. And for an SSD, that sounds maybe not brilliant, but this is a good SSD, so a solid state disk IO time. Now, let's add these statistics here. And if we now look at the overall times and we add these times of the lower two columns, what we then can see is that the execution time, this is the execution time, potentially not a full time, but probably in a lot of cases it is. If we take that as 100%, then the total time spent in doing physical IO to satisfy this query is 58%. So by going through these layers, and obviously, if you know where to look and you know these names, you can work this out faster. But overall, it's good that we can, in this way, perform a test case and say, okay, in my case here, I'm 58% IO bound. I now know this. And that's not because I am having slow IOs, or at least not an average, but still 58% of the total time for this query is performing IO. This doesn't stop here. Actually, tablet servers perform what is commonly called buffered IO. And buffered IO means that whenever we perform an IO request, we perform it in the Linux and Unix standard way. Oh, and Windows even, but we do not work on Windows, but in the standard way, which means it allows the operating system to cache the read and writes. This means that by doing this, the operating system plays a fundamentally important role in the IO latency. Now, with this in mind, we ourselves use Node Exporter, which is part of the Prometheus suite, as the exporter for the node statistics. And the node statistics are simply the Linux level statistics. And in general, we advise to use Node Exporter with Yugabyte DB clusters in order to expose operating system level statistics. But it is not mandatory. A Yugabyte DB cluster will perfectly work without Node Exporter, but Node Exporter provides a lot of statistics which are quite fundamentally important. And we will be looking at IO here, but obviously it gives all kinds of information about CPU, IO, and lots of other things. Node Exporter does export a lot of data, and with that, it doesn't only export the traditional statistics, and with traditional statistics, I mean the statistics which are commonly used with the SAR, the Systat SAR suite, and using IOStat and using SAR and lots of other tools. But it also exports all kinds of other statistics, which are able to give some interesting insight. A well-known statistic is node disk reads completed total. And if you're not overly familiar with Node Exporter, this might not mean a lot, but this simply means the IOs which are completed by a given block device and which means this statistic will give you and show you data which you also could see with IOStat or SAR-min-D or SAR-min-B, etc. The total number of block device physical read IO request or IO requests in general. However, there is a statistic which is called node XFS read calls total, which is the number of read requests which is served, including cached file system requests. And that is really, really handy to know, because this allows you to see the number of logical calls to the file system. And by looking at no disk reads completed total, you know the actual physical reads. So you can work out on how effective the page cache in Linux has been. And that is quite new, because I don't see that happening a lot. Caveat, there is an important caveat, and probably you've worked it out for yourself, but it says XFS. So you need to run XFS to get this statistic. And we use XFS in all our Linux machines. So I'm not sure if you're using EXT, which is the default Linux file system, Btrfs or anything else, if it will show these statistics in Node Exporter. We use XFS, and there we've got this statistic. But this is quite interesting to know. Now, let's look at this snapshot again. And by the way, as a small diversion, I hope you see that by taking these snapshots, which contain all the information, and then by building a logical case for yourself, and then investigating the statistics, I hope you see how you can use the snapshots as a source and then continuously go back to more snapshot data to create a logical overview and a logical thought process through what is happening with a certain machine. And that is the whole purpose of it, so that you can build a logical understanding and create a foundation by actual figures and truths about what is happening. So let's look at RocksDB SST read micros again and look at these times. If we now take node disk reads completed and at XFS read calls total SDB1, we see that each of them has had physical reads, and the physical reads are actually pretty much on par with the requested reads from the tablet server. And we see XFS read calls complete calls total, which is a little higher, approximately roughly 1,000 higher. Now, this is the amount of logical IOs, this is the amount of physical IOs. These IOs map to SST reads, but there is some caching going on. So we cannot tell if these were all physical reads. So if the physical reads, which we see here in no disk reads completed, maps completely to this, there is no evidence to tell that. But obviously the majority must have been. That there is also no way around that. And this is a counter. So this is a counter for the number of occurrences. And this is the amount per second. So we've got no timing. Another caveat for RocksDB SST read micros, if you're using this same drill down on a running cluster, then this running cluster might perform write work, and this might lead to a mem table which is full. And if the mem table is full, it will be flushed to disk. And if enough SST files are flushed to disk, it will trigger compaction. And what compaction does is it reads SST files and it compacts, it puts them together. It filters rows which are timed out. So if there is a change which is beyond the 15 minutes, which we've set as timeout, which is configurable with a G flag, which is our name for a parameter. Then we can filter it out with compaction. If we've marked, if we deleted rows, then these rows are not deleted, but these have been given a delete marker, which we call a tombstone. And during compaction, we read the tombstones. And if the tombstone is older than this 15 minutes of time, which we've set as a timeout for these, then the tombstone will also make these deleted rows be actually deleted. So this is kind of not equal to, but kind of what Postgres vacuuming does. But this happens completely autonomously. And if at a certain point you stop making changes to a table, it means you're not writing in the mem table anymore. So compaction will never be triggered. And for Yugabyte DB, that's absolutely not a problem. We do not have the same problem as Postgres, which is transaction ID wraparound. So you have to perform vacuuming in Postgres within a certain time, or else this transaction ID wraparound can happen. And we do not use transaction IDs on the Postgres. We do not use the transaction mechanism on the Postgres level in that sense. So we absolutely do not have that problem. Now, but when that compaction happens, then what it does is it uses the rows which are already in the RocksDB block cache, and it invalidates them, and it reads blocks which are not in the block cache. And by reading these and then performing the compaction, it writes out another file. This reading also counts as SST reads. So if you're using this statistic on a running database, then this could include compaction. So therefore you have to be really careful. So there is a risk that you need to quite well understand what's going on. But still, knowing what is actually going on is the only way that you can make actual foundational decisions about architecture and how to create your setup and how to form your database. So I would say that's still fundamentally important. But okay, let's say I see, sorry, is Yugabyte, I see I've got some questions, so I will look at them. This first question was for some time back. Is Yugabyte DB support for Drupal or WordPress application? I'm not exactly sure what that question is aiming. If we're using Drupal or WordPress, I couldn't tell. Sorry, I don't know what we're using underneath. And the compaction is that packed rows. Packed rows means that instead of storing individual columns of a row in distinct documents, a packed row means that we're using the information, the data from different columns, and store them in a single document. And that is where the name packed comes from. So that is what is a packed row. So compaction and a packed row are two separate things. Compaction is the process of rewriting SST files and filtering out anything that has timed out, essentially. And a packed row is a specific way of writing a row in the first place. So hopefully that makes sense. Otherwise, I believe there are some blogs about it. Search for Yugabyte DB in compaction and packed row. Sorry, search for Yugabyte DB and packed row, and then I think there will be a blog from engineering describing it. But the essence is that it's an internal optimization which can happen at write time. It doesn't need compaction. It can happen at write time already if you're writing a row. What can happen is that if a packed row, if columns are changed from a packed row, then these row information will start to scatter out over in multiple places, because we only ever add to the mem table. So if a row is fairly old and we change a value and it's a packed row, it will still only create this new value in the mem table. So then a row starts to be spreading out more over the RocksDB mem table and SST files, and then compaction potentially can glue them back together again. Okay, so what I've just described is be cautious with RocksDB SST read macros, but in this case, I was running on an idle server, and I run a single query in isolation. So and I did a read request. So SST read macros absolutely was only for my query. I see these figures, and based upon the node exporter statistics for logical I/O and physical I/O, I can see that the gist of it is performed actually against the block device. So it wasn't cached on the Linux level, but it was cached. It wasn't cached on the Linux level. It actually performed an I/O against the block device. So it performed a physical I/O. Now, what if, by doing this, obviously, if Linux has a chance, Linux will cache these blocks for me. So what if Linux will cache these blocks for me? And what we've seen in the previous slide is that these we're already using the RocksDB block cache. So what if I'm just executing it again and hope for the operating system cache to perform its function? And this is how that looks like. I performed it again, so I've got another begin and end snapshot number. Of course, what happened here is that I took a snapshot again, performed the select star from large, and then performed the snapshot again, took note of the snapshot numbers, use the snapshot numbers here, and use the exact name, statistic name match. Now, what we see is RocksDB SST read macros has the same numbers, so there is no further caching going on in Yugabyte DB. We still need to perform more than 1,000 physical I/Os from the perspective of the tablet server. Looking at the physical layer, at the operating system layer, looking at node XFS read calls, I also see the same number of logical I/O calls. However, there are no disk reads completed calls visible. These are completely gone. In other words, this shows that I'm now not performing any physical I/Os anymore. And we can also see this by the averaged, well, you can see it by the total time too, if you remember the time from the previous slide. But if you look at the average time gone to 2 microseconds. So despite the fact that from the perspective of the tablet server, we still perform physical I/O, we actually didn't perform physical I/O because we could take advantage of the caching of the operating system. In other words, this has a really important implication. It is really important to keep note and try to keep memory available for the operating system, essentially not doing anything in your calculations in order for the operating system to perform caching too, in order to let this happen. If you use up all the memory and there is no memory left, and obviously the operating system can't do its caching, and and that is a chance, and it has to perform this caching if it's performing physical I/Os. So it is really important that the operating system is given some room to perform its work on. However, I've done something, a select statement in complete isolation. Perform is not always strictly sequential, as we saw. It could perform work which is actually performed in parallel. And Frank has been touching on it for a while in his presentation. The select star from table, which I've just showcased, is doing an serial execution. So the execution is one-on-one. The first one equals the perform thread, and the last one is equals to the actual work. A select count star is executed in parallel. What it actually does is what Yugabyte DB calls an aggregate pushdown. So it creates the work, it sends it to the perform thread, and the perform thread pushes down this work to the tablet servers, which then perform this work. And it is and all the tablet servers on this work at the same time. Other pushdowns will also perform the work in this way. And this is how that looks like. I've here now performed a select count star from large. My total time is 1.5, let's say 1.5 seconds, and it's one execution, so average and total time are identical. The select statements take 1.5 seconds, and there is a new statistic here in the PG gate layer which says aggregate pushdowns, and aggregate pushdowns also says 1.5 seconds. So all my one executions are do spend this time. If I look in perform is slightly more. However, we see catalog cache misses. So it probably had to go out to the master server and look up some stuff. So this time is slightly more here. That is the reason for it. And we've got a bug open for this. We currently do not time catalog cache misses. So looking up something which is not stored in the catalog cache in a backend yet. And if we look at the YB client time, so the time in on how the executions are spread out over the different tablet servers, we see here that YB client remote is actually spending way more time than PG client service perform. And local is spending this is 1.4 second, which is, this is also roughly 1.4 second. And if you divide this is slightly less. So it probably takes the time of the longest taking individual parallel executed SQL. Having said that, writes are executed in complete parallel as far as I can see. And if you're performing regular single row writes, which a lot of clients are doing, then writes are essentially serial. So that's not a problem. And if you're spending small amounts of writes with multiple rows, you are also probably just performing them in serial, because these, if you batch up a few rows which are not too big, they all fit in the same RPC packet, so you don't notice anything. If you perform and create table as select, and you create 1 million really large rows like I did with repeat X 500, so that's a lot of X's in a single row. And of course that data is silly, but it's just to create space which is taken for the row. But then this action execute creates multiple RPCs, and these multiple RPCs are from the start all executed in parallel, and that makes perform in perform they are all measured as if each individual request in perform was executed serially, whilst in reality they are executed in parallel right from the start. The probable reason for that is because at write time, it's yet unknown where the row will end. I'm not 100% sure about that. I need to read the code to understand how that exactly works. But That's probably the reason, but they could potentially be sent in parallel. In other words, sadly, it means that you cannot just have a really busy cluster doing lots of things, take 2 snapshots, and then be 100% sure that all your time in Perform is the actual time which is spent by all the clients in on the tablet server layer. There could be some deviations from it, although if you're doing typical OLTP type queries, you probably Perform is the actual time. There is no guarantee because of this last caveat, which potentially might make them parallel. So that's a bit sad, but that's it. Okay, so I've sent a lot of details to you. What I'm saying is, take this presentation. This presentation will be made available, and repeat the test and try to see if you see other things or not. Hopefully, and probably you will not see other things. Look at other statistics. Do not apply a filter and look at all the statistics. And then you, point one, know why I filtered, because you get a lot of data. And point two, you see the actual statistics from your own local cluster, and you can start working them out. Then going to the conclusions, YB-Stats allows you to take I strive to take all available data, but there is some data which I currently do not store, but YB-Stats allows to take most available data from a Yugabyte cluster and persist it. This way you build facts and you build history. And YB-Stats is used by our support and development. So if you're using it, and you've captured an issue in it using 2 snapshots, support can readily use it already. So that is really helpful. And then you've got all the statistics and metadata that the Yugabyte cluster contains with it. So that is really handy. And SQL backend communicates to the local tablet server. This is at least true starting from version 2.13.1. That's the version I'm aware of. Any logon requires master communication. Currently, that is the current state. As far as we go, we strive to make this better, but this is the current state. And this master communication, again, is proxied by the local tablet server. So the backend, which is created, talks to the local tablet server, and the local tablet server fetches the catalog data from the master. Okay, I see another question. The parallel operation, can you set the parallel degree? No. The way the parallelism works is that it will simply spread out to the number of tablet leaders which are involved in the object which is used in parallel. That is how parallelism works. And to be honest, I'm quite happy with it, because what I saw, historically, I spent 10 years doing internals in Oracle databases. And what I saw in these 10 years is a huge oversubscription of parallelism, because there are lots and lots of people who think that you can drive parallelism, that higher means more. And hopefully, if you've paid attention to a lot of the things I said, in a lot of cases, less is more. You need to keep resources available so that anything you do is actually backed by available resources, instead of not being backed by available resources, and you have to wait for memory or SQL or a CPU to be available. And also in Yugabyte DB, it's really easy to completely oversubscribe memory or CPU. And in that sense, if we would make parallelism changeable, that would also potentially could lead to lots of oversubscription. I'm not sure if we will be making Postgres level parallelism available, and Postgres level parallelism will then means that you simply create or use multiple backends to perform your task. That then again gives you great opportunities to completely oversubscribe the cluster, but we do not use Postgres level parallelism at this point in time. And I'm not sure how helpful it actually would be based upon everything that I said before this. So hopefully that gives an answer. The very first access to a database after startup. So again, this is really the very first one for any database for a given postmaster. It's really only the first one. So if you then execute things in 10 sessions for 10,000 times, it's neglectable. But if you're performing some tests and you're only executing a few SQLs with a just created connection, with a just created database, or a just started up Yugabyte cluster, then this first access, which is quite much slower, might completely pull your statistics upside down. So be really careful about that. Any execution requires catalog data. Now, this is not as grim as it sounds. You only need to reach out to the master once to fetch the catalog data, and then it will be cached in your backend. But that data is required. Again, this is identical to Postgres as well as the extra work for the very first connection. So, and that also, I'm also summarized the last row, which is catalog data is fetched from the master leader and cached. The YB cluster keeps a lot of statistics about what it's doing, and YB stats is what takes advantage of these statistics. We provide these statistics with the web interfaces at 7,000 and 9,000, and if you're using the our web interface, Yugabyte Anywhere, Yugabyte DB Anywhere, then this is using exactly the same statistics. So I'm not using a secret magic point of statistics. These are just the statistics that we provide, and they are also available as Prometheus statistics. So you can just put your Prometheus node to it, and it will fetch it. The statistics do not give a single level view of the cluster. Well, no database actually does, but just to be absolutely sure. So you see general performance statistics, you see read level statistics, and you see actual physical I/O statistics, for which the previous two also contain this information. So there are multiple levels of activity that these time, and you need to understand a bit about where these fit in to paint a picture of it. However, using the statistics and an understanding of how work is performed allow you to tell where time is spent on. And in Frank's talk, somebody was asking about a wait interface. We use Postgres. Postgres has a rudimentary, almost non-existent wait interface, which we currently do not use. And in essence, it's not really that much in use in Postgres too. Some plugins there use wait state sampling, and at current, we do not set a wait state, but this will be changed in the future. I hope. I'm actively working on that actually. Using the statistics in the master and the tablet server, you can understand where for principal activities time is spent on, but they do not provide an overall overview of where time is going. Yeah, I would like that to be, but that is quite comprehensive and quite hard to get. So at current we don't, and we just time what we think are primarily important activities, and we time these independently. Yugabyte uses the operating system cache, also known as the page cache. So that is really important to realize, which means you need memory to be available to allow this buffering to take place, because any I/O, even if no memory is available, needs to get a page and store it in the cache, even if that cached page is immediately abandoned because there is a shortage of memory. You've asked for buffered I/O, so you get buffered I/O. You get what you ask for, even if you don't explicitly ask for it. That is how it works. And there's a lot to say about that, but that's how it works. And lastly, different queries might work differently. So if you do not use an existing cluster where all kinds of queries are running, because these might interfere and make it really hard to understand what's going on. If you have a problem query and you've isolated the specific problem query, take hopefully, or as good as possible, a completely idle cluster and test out your SQL and see what it does, because then it gives you truly the information for executing that SQL. So that's it. Are there any further questions? I will make the slides available, and this is recorded. Well, I'm pretty sure this is recorded. So are there any questions or remarks? Okay, I see a question here. It didn't pop up, by the way. Question for indexes. How are they stored and accessed? Memory disk. Essentially, I think Frank made a good description of memory and access to data. We store LSM tree. We store LSM trees. So it is really, really easy to think in B-tree and in blocks, but we're not using that. We store things in sorted logs with skip lists. So we know where to go using the skip list, and that's either in memory or on disk. And in that sense, a table in Yugabyte is a table which is organized, which has the full rows organized by its primary key, and therefore we can quickly skip to the correct row. And an index essentially is the same. It's only ordered by a different primary key, by a different key in which it's ordered, and that is how it works. So you really have to think differently about that in that sense. For LSM trees, I would say that there isn't really too much of a difference between memory and disk. It's only the locality which determines if it's on memory or disk, and the accessing is quite different, as Frank has described. So hopefully that answers it. Oh, no, not sure. Okay, so that's it. Are there any other questions? Anything else that anyone wants to know? Thank you for your kind words. Yeah, and please, I've put a lot of information to your side. If you're interested in this, what you need to do is Download YB stats and experiment a bit with what you're seeing. And I'll be completely honest with you, there are a lot of statistics for which I don't know what they are. You need to discover, you need to read. Some of the statistics are described, and in that way you need to extend your knowledge about how it works and work in this way. But the reward is big because you will be able to tell if something is actually happening or not. Okay. Thank you, everybody.